Inertia is the tendency of an object to resist any change in its state of motion. In simple words, an object does not easily want to start moving, stop moving, speed up, slow down, or change its direction. This resistance to change is called inertia. Inertia is not a force. It is a property of matter, and the amount of inertia an object has depends on its mass. The greater the mass of an object, the greater its inertia, and therefore the greater the resistance it offers to a change in its motion. The relationship between mass and inertia is very important in Newtonian mechanics. A low-mass object has relatively low inertia, while a high-mass object has relatively high inertia. For example, a small feather has very little mass and therefore very little inertia, while a heavy anchor has a much greater mass and therefore much greater inertia. This means that a larger force is generally required to produce the same acceleration in a more massive object. This idea can be understood directly from Newton's second law, which is written as F equals ma. Rearranging this equation gives acceleration equals force divided by mass. Therefore, if the same force is applied to two objects, the object with the smaller mass experiences greater acceleration, while the object with the larger mass experiences smaller acceleration. The clearest example in the image is the comparison between an empty shopping trolley and a heavily loaded shopping trolley. The empty trolley has a relatively small mass, so it has less inertia and can be accelerated easily. If you push the empty trolley with a certain force, its velocity can change quite quickly. Now imagine applying exactly the same force to a trolley filled with heavy groceries. The loaded trolley has a much greater mass, so it has greater inertia. It resists the change in its motion more strongly, and the same pushing force produces a smaller acceleration. This is why a heavily loaded shopping trolley feels much harder to get moving than an empty trolley. We can understand this quantitatively using F equals ma. Suppose the same force is applied to an empty trolley and a loaded trolley. If the empty trolley has a mass of 10 kilograms and the loaded trolley has a mass of 50 kilograms, the loaded trolley has 5 times the mass of the empty trolley. For the same applied force, the acceleration of the loaded trolley will therefore be 5 times smaller. This demonstrates an important relationship. For a constant force, acceleration is inversely proportional to mass. Increasing mass increases inertia and makes it harder to change the object's velocity. The image also shows that inertia can appear in different situations. An object at rest has a tendency to remain at rest. This is sometimes called inertia of rest. For example, when a car suddenly starts moving forward, the passenger's body tends to remain in its original state of rest. The car moves forward underneath the passenger, so the passenger may appear to move backward relative to the car. The passenger is not actually being pushed backward by some mysterious force. Rather, the body resists the sudden change from rest to forward motion. The car seat then provides a force that accelerates the passenger along with the car. Another important example is sudden braking. When a moving car suddenly brakes, the car's velocity decreases rapidly, but the passenger's body tends to continue moving forward because of inertia of motion. The passenger therefore moves forward relative to the car. This is why passengers can be thrown forward when a vehicle stops suddenly. A seat belt provides an external force that changes the passenger's motion and brings the body to rest along with the car. The seat belt therefore plays an important role in protecting passengers by controlling the effects of inertia. Inertia is also responsible for an object's tendency to maintain its direction of motion. If an object is moving in a straight line, it tends to continue moving in that same straight line unless an external resultant force changes its direction. For example, when a car turns around a corner, the passengers tend to move toward the outside of the turn because their bodies tend to continue moving in the original direction. The car changes direction, but the passengers' bodies resist that change. A force from the car and the seatbelt is required to change their direction of motion. The image also shows a book resting on a table. The book is affected by its weight acting downward and the normal reaction force from the table acting upward. If the book is stationary and the upward normal reaction is equal in magnitude to the downward weight, the resultant force is zero. We can express this as N equals W. Since the resultant force is zero, Newton's second law tells us that the acceleration is also zero. Therefore, the book remains at rest. This is an important example, because zero resultant force does not mean that there are no forces acting on the object. It means that the forces acting on the object balance each other. The connection between inertia and Newton's first law is especially important. Newton's first law states that an object remains at rest or continues moving with constant velocity in a straight line unless acted upon by a non-zero resultant external force. Inertia explains why the object behaves this way. An object naturally resists changes in its state of motion. If the resultant force is zero, there is no acceleration, so the velocity does not change. If the object was initially at rest, it remains at rest. If it was already moving, it continues moving with constant velocity. It is also important to remember that inertia is not a force. In an A-level physics examination, saying that inertia is a force would be incorrect. Inertia is the tendency or property of an object to resist changes in its motion. Mass is used as a measure of an object's inertia. Therefore, when we say that a heavy object has greater inertia, we mean that its motion is more resistant to change because it has greater mass. The master's summary in the image can therefore be understood as a chain of connected ideas. Mass is a measure of inertia. Greater mass means greater inertia. Greater inertia means greater resistance to a change in motion. When the resultant force is zero, the acceleration is zero, so the object's state of motion remains unchanged. If it is at rest, it remains at rest, and if it is moving with constant velocity, it continues moving with constant velocity in a straight line. The most important idea to remember is that inertia describes resistance to a change in motion, not resistance to motion itself. A massive object can move very quickly, but changing its velocity requires a greater force compared with a less massive object. For example, a heavy truck can travel at high speed, but bringing it to rest requires a significant force because its large mass gives it large inertia. Similarly, accelerating the truck requires a larger force than accelerating a much lighter car by the same amount. So, the key relationship is simple. Greater mass means greater inertia, and greater inertia means greater resistance to changes in motion.